I'm sorry. And here is the outline. First, I will introduce our work about the global propagation of LSTID at mid and low latitudes and the comparison of the TID with us over North America. And then I will introduce the observation of the fine structures of MSTID, especially caused by the rocket launches in China. And here is the one example of the early work of observation of LSTID. LSTID was firstly observed through some single stations, and then through, for example, a chain of stations. This is an early observation of them through the chain of ISR radar chain. And the primary source was revealed was the enhancement of auroral electric jet or the particle precipitation. Recently, there are some unformed sources such as the equatorial electric jet or the secondary waveform, but this is yet to be observed and confirmed. And as seen from this figure, the stations are spaced by a distance of about more than 1,000 kilometers, and that was comparable with the wavelengths of the LSTID. So we don't know what happened to LSTID during this area. So another way of observation is to set up a local array to observe this LSTID, but that is also a localized observation. And from the late 1990s, the GNSS network provided maybe this advantage to observe LSTID. And there is some disadvantage. For example, the GNSS observation provides TEC, and this is integral measurements, and it cannot provide high profile. But the density distribution of these receivers provide a unique way, other than other any measurements, to observe TID. And there are some localized GNSS networks, such as IGS and CORS in North America, and GeoNet in Japan, and CMO NOC, cross the movement of network of China in China. And we use this network to do some observation through the years. And here is the method. And I will briefly introduce the main difference between our method with others is that because in China there was a latitude variation of the background TC larger than that in North America. So we express the background TC as a function of as a two-order function of local time and latitude, and then we filter the data and get the perturbation of TC, and then we identify the TC through some published criteria. And first, we observe LSTID through a medium storm on May the 28th in 2011. And this medium storm occurred with a DST nearly minus 80 NT. And here is the TID we observed. Just the onset of the substorm here initiated a slow speed TID in the northwest of North America. And then this time it was around midnight. And 1 hour and a half later, a second TID arrived in China in the local time of dusk. And 6 hours later, a third TID arrived in China in the local time around midnight, just here. And both TID over China disappeared in a region with the magnetic latitude of about 30 degrees. That equals to magnetic latitude of about 19 degrees. And our ionosonde chain also observes this TID, and this is the ionosonde chain, and this is the height, the vertical height variation at various working frequencies, and we can see the fluctuation of the vertical height as a function of universal time, and the fluctuation propagate southward through this side until this side. But we cannot observe the successive perturbation in highland in the southmost side. And hours before we detect the third TID in China, we observed the TID through the Japan's GeoNet. So this TID, because this is LSTID propagated southwestward, so this TID propagated from the north of Japan to China. And during the same medium storm, we observed some two northward propagating TIDs as expressed in this figure and this figure. And the perturbation amplitude is rather smaller than those of the south propagator one. And both of the northward TIDs suffered severe dissipation. And compare with the two types of the TID, we found the poleward TID exhibited a narrow latitude range and a smaller amplitude compared with the equatorward ones. And the elevation calculated from the dispersal relation is slightly higher than those of the southward ones. So this indicates that the northward TID might be caused by some localized source rather than on the other side of the aurora region. And in China, the TID was characterized by a severe dissipation, and this is the relative amplitude, and the relative amplitude decreased from more than 5% to less than 1%. And aggregate author Richmond is here. 2 weeks ago, I discussed with him with his equations, and in an early work of author Richmond, he come up with an energy dissipation equation, and the dissipation was related to the molecular viscosities and the heat conductivities, and these two factors increase the dissipation, increase quickly with propagation time. So these are the main cause of the dissipation of these aggregate waves, and the gravity waves caused the TID. We can observe this TID. And another factor is the ion drag, and we can see the ion drag is related to this one. And the ion drag caused the dissipation increase linearly with time, and so is smaller compared to those of this one. The ion drag dissipation is proportional to sigma 1 Peterson conductivity, but is inverse proportional to the neutral density. As we can see, there is an enhancement of TC during this time of about 30 to 100%, but on the same time, there is an average increase of the neutral density of up to 75%, as observed by Trump subnet by one of my colleagues, Lei Jiuho. So the dissipation due to the ion drag cannot be ignored, but is rather small than this one. And in our observation, another influence is the uplift of the ionosphere. We can see the uplift of the ionosphere during this the storm time. There is about up to 70 kilometers uplift of the ionosphere. And the simulation shows that the energy of the HWs mainly focus on this height. So when the observation height increase, the energy can be observed by the ionosphere TC decrease. So this can also influence our observation. And next, we conduct a comparative study of the LSTID over North America and China. And here, this is a global distribution of TC. We excluded the local time variation. And you can see there are three GNSS dense distribution area, North America, Europe, and East Asia. And these two regions are located in the mid and high latitude region. And in China, this is located in the mid and low latitude region. These GNSS networks cover some typical mid, high, and low latitude regions. So we conducted the comparative study to observe the latitude difference. And we observed the data with a duration of 21 months. And this we need to analyze a large data set, and it takes us several months. We identified a total of 390 LSTD TIDs in China, and another 363 events in North America. And all these TID can be classified into three types: the Southward TID, the Westward TID, and the Northward TID. And as to the Northward TID, we only observe two of them in North America. It mainly occurs in China. And here is all the events and in North America and China. And the blue dot here is the Southward LSTID, and the red one is the Westward TID. The Westward TID was characterized by a local time focus, and nearly all of the Westward TID occurred during the time of the sunrise. Here, sunrise, and here, sunrise. As to the Northward TID, we can only observe two of them in North America, but we can observe more than 20 of them in China. Most of the TID are propagated southwestward, as seen. This is the as a function of the variation of the propagation azimuth as a function of local time. And we can see Westward TID, Northward TID are mainly observed in China. And as to the Westward TID, this is the observation of one of my students. And this black line is the solar terminator. So we can see the occurrence during, it occurs during the local sunrise. And the propagation direction is perpendicular to the solar terminator. And we can also analyze that is irrelevant with the geomagnetic disturbance. And there are two features of the southward TID. First, the westward shift from south is about 19 degrees larger for LSTID in China than in North America. So in China, it propagates more southward than in North America. So the Coriolis force is accounted for the possible difference. And secondly, in both regions, there was a local time variation. The westward shift from south is 30 degrees larger at night than during the daytime in both regions. And for the southward TID over North America, this is an example. And we can see the first phase front propagated southwestward, and then a second phase front propagated nearly southward, a little westward. So this indicates a moving of the aerial source or the change of the aerial source. And the wave fronts can be as wide as more than 4,000 kilometers. And this is an example of the southward LSTID over China. The TID propagated to the southmost of China. And most of the TID occurred 1 to 2 hours later than over North America. And the TID in this region undergone severe dissipation. And here is the dual variation of the occurrence rate. Again, this is the westward TID. It occurs during the sunrise, local time of sunrise. And this is the southward TID. And this is the mean value of KP index during our observation time. You can see this is a minimum during this universal time and a maximum during this time. And in North America, the occurrence rate maximum is near the maximum of the KP index. However, in China, there is a time lag of the maximum here, and the maximum of the occurrence rate lasted several hours till the local time of midnight. This maybe because there is a local dual variation of the local ionosphere may affect the observation of TID, because during the local time of night, the ion drag is smaller than those in the daytime, so it makes it this made it more convenient to observe TID at night. So, in addition to the geomagnetic activity, there should be other factors such as the local variation of the ionosphere that increase the variation of the creation of the LSTID over China. And this is the seasonal variation of the propagation direction. The most obvious variation is the westward TID. We can see a seasonal variation in the summertime in both regions because they are both in North Hemisphere. The westward TID propagate with a smaller azimuth than those in winter time, and this is related to the deviation of the solar thermometer, seasonal deviation of the solar thermometer. And here I introduce the observation of the multi-LSTIDs over China. And the motivation of this study is to find the spatial and the temporal variation of the multi-LSTID structures. This is an example of the single LSTID, and we can determine the wavefront through the TEC perturbation maximum or minimum. But in some cases, there are multiple propagate LSTID. This was defined by the simultaneous appearance of the LSTID during in the same region. And here we can see some phase fronts propagate southward, and other fronts propagate northward. It's very difficult to distinguish one TID from another from these figures, because there seems chaos. So our method is to set some lines along the meridian or the zonal line, and to make some diagnose of the TID, like computed tomography to examine our body. And here we totally observed 3 groups of the multi-TID, and this is the 3rd group. We set some lines along the zonal line and along the meridian. And here we can see this is from slide B, and this is the TEC perturbation as a function of local time and propagation distance. We can see some southward TID in the upper side, and we can also see some northward TID. But unfortunately, there is a lack of data. And for the slide C, note that slide C locates 1,000 kilometers west of the slide B, and the southward TID nearly disappeared. So this indicates that the southward TID, although they propagate from the Aurora region to the mid and low latitude, there is a limitation of their propagation range. And it's clear that the northward TID, there is a distortion of the phase front of the northward TID. And the distortion implies that there is a velocity change of TID in this area. This phenomenon cannot be explained just by this figure. Now we can see the TID on 3 zonal slides. And for the slide D here, we can also see the TID. And in the first stage, it propagates just the northward because the phase front nearly vertical to the x-axis. And then after this time, it propagates westward. And in slides E and F, all the phase fronts propagate northward or southward, and no westward or eastward component. Under careful analysis, we can trace what happened to this northward TID. In the initial stage of TID, which was observed by slides D and slides B, this is where the northward structure was made up of a northward LSTID and a westward one, by 2 northward TID, a northward TID and a northwestward one. And their fronts, both of the northward TID fronts, were mixed together. And this yields phase front with broadened Ys. Here, the Ys is rather broadened and an enhanced amplitude. And the mixed fronts moved northward at a distance of more than 1,500 kilometers, and until at this time. And then the phase fronts were separated due to the different propagation direction and velocity. After that, the westward one continued to propagate another about 400 or 500 kilometers until they were dissipated due to severe dissipation in our North China. And the northward one continued to propagate here to latitude to this region, and can be observed by slides F. And here we examined all the propagation features of these multi-TIDs. And this is the Beidou geostationary satellite TC observation. Our institute have a chain of Beidou observation here, and we can see this only provides some time series, and these are 3 groups. I didn't introduce these first 2 groups, and we can also see the encounter of the northward and the southward TID, and the enhancement of the amplitude, and then the 2 phase fronts propagate in the opposite direction after encountered. And this is the third one, but from the time series, we can only see 1 northward TID and 1 southward one. So the time series observation lacks some information. And the second part of my study is about the fine structures of MSTID. And we do some work about TID excited during the solar eclipse, during the associated to the atmospheric instability, and during the meteorite blast in Russia, and also some CIDs called seismic atmospheric disturbance after the strong earthquake. Due to the time limitation, I here only introduce the MSTID excited by the rocket launches. It's well known that when an object is moving with high velocity, it's possible to excite atmospheric waves. And this high-speed source, some natural source includes the moving of the solar thermometer or the moving of the eclipse umbra. And there are some sonic source, artificial source, such as the moving of the rocket, the missile. And I here cite some very early work. And here is an example. This is the ionosonde observation of the TID after the rocket launch in Florida. This is some early results. The excitation region, as studied by Noble in 1990s, he found the region is located in the ascending stage of the space shuttle, because in the ascending stage, more than 70% of the energy was released during this stage. After that stage, the rocket mainly moved horizontally. And in this stage, the rocket it releases smaller energy than the ascending stage. And some propagation mechanisms were also proposed by some authors, such as Abramovich. And this is a recent observation before my paper in 2014 is by Kakinami, by a Korea scholar. And he used the Japan network to observe the TID excited by the North Korea rocket missile launch. And there is not obvious, the feature is not obvious. Maybe this is because there is a low elevation angle here. And this is the world's main launch site. In North America, there are 3 launch sites, and most of the early work of TID due to rocket launch was observed during here. And recently, some people observed TID during this site in California. And in China, there are 4 launch sites, Taiyuan, Jiuquan, and in South China, Xichang, and another site in the Highland Island. Because in China, most of the rocket flies in this direction. For example, in southward or southeastward. So the rocket passed the region with a dense distribution of the GNSS network. So this provide a good opportunity for us to monitor TID caused by China's launch event. And this is the launch of Shenzhou 10 spacecraft. And this is the figure. And the rocket flies, the rocket weighs about 450 tons. And it flies from Jiuquan, this side, eastward to the Yellow Sea. Within 10 minutes, it arrived here and burned all the fuels. It moved with a very large velocity and with a rocket flight range of more than 2,000 kilometers. And we used the GNSS network from both the Chinese Meteorological Administration and the China Seismic Administration to observe this event. And here is the TEC time series. We can see during this red line indicates the launch of the rocket. After the launch, there was a decrease of the background TEC of up to 5 TEC unit. And before the decrease of TEC, there was some smaller amplitude perturbations here. And this is the TID caused by the rocket launch. And we use a 0 phase shift band pass filter to filter the original this data, and then we get the perturbation TID. And here is the perturbation. We can see the TID propagate away from the trajectory away, and with a decrease of the amplitude. And the time series was composed of large amplitude N-shape propagation. This is a shock wave, and successive smaller size perturbation. and this is the acoustic guard waves with a period of about less than 12 minutes. And it's not clear. There are some night black nights here indicates the same DTC series before this day and after this day, and there are no perturbations in other days. And this is the two-dimensional evolution of TID during the rocket launch. And this is the rocket trajectory. And we can see the phase fronts was generated in this region, and most of them propagate southwestward to a distance of more than 1,500 kilometers near Wuhan. And other parts of the phase fronts propagate northward, but the amplitude is much smaller than the southward one. And here is the perturbation as a function of local time and propagation distance. And in the north of the trajectory, there are some phase fronts here with very small amplitude. In the south one, this is the N-shaped shock, and this is the successive acoustic gravity waves, both dissipated, and the shock wave dissipated more quickly than other one. Secondly, we observed the TID excited by the Long March 4B, and this is the profile of Long March 2F, just we published in 2014, and the rocket reached a height of about more than 300 kilometers, just in the ionosphere height. And for Long March 4B, its real height is near 800 kilometers. So just the rocket just crossed the ionosphere, and the rocket was launched from Taiyuan and flies southwestward and sends the satellite to a sun-synthesized orbit with a real height of this value. And here is an example of the two-dimensional evolution of TID. It's not clear there is a shock wave along the trajectory, and it's clear there are some circle waves here, as the circle wave was previously observed by other authors, observed from California, and circle wave and shock wave. And the wave is more clear in this figure. We see the slides down here, and we can see this is the shock waves. And the shock waves follows throughout the trajectory from here to here. And there are some smaller amplitude circle waves with a period of about 2 minutes or 7 minutes here. And the circle waves can be divided into 3 groups here. And through these slides, we can see the east-west extension of the shock wave. The shock wave, unlike the wave we observed just now, the east-west extension is rather smaller here. The shock wave just propagates about less than 300 kilometers in the east and west of the trajectory. And as for the circle wave, they propagate more than 1,000 kilometers. And as to the circle waves, they propagate at a velocity of 900 to 1,000 meters per second. And this is the period. And the center of the circles locates just about approximately here in somewhat south of the launch site. This is because the circle wave is likely to be excited by rocket during this ascending stage. And after the ascending stage, the rocket propagates mainly horizontally and accelerate with the increase of the horizontal velocity. And in this stage, it mainly excited the shock wave. And then the last, we can observe the TC depletion. The TC depletion here is up to 10 TC unit and is very large. And it lasts about 1 hour and a half. And we can also see the movement of the TC depletion area or the ionosphere whole. It moves slowly westward with a velocity of about 80 meters per second. And one of my missions here is to use the model to simulate the decrease of TC and also the drift of this hole. Okay, this is the summary. LSTID at high latitudes has good correlation with the geomagnetic activities, but at mid and low latitudes, the variation of the ionosphere represents an important factor that affects the dual variation of the LSTID. Also, MSTID associated with shock wave and circle wave were observed by us during the China's rocket launch, and westward drift of TC depletion area can be found. Okay, thank you.
So in this MSTID after the rocket launch, so the south side of the trajectory seems to have a stronger amplitude, and the north has less. Smaller amplitude. Do you know why? Is it always happen this way, or just this event? Or do you expect it is always like this?
This north-south symmetry was observed by many authors. For example, some Japan authors found after the volcano eruption, the acoustic gravity waves also show such north-south symmetry. And after the 311 tsunami, the TID also see such variation. Until now, I have no confirmed examination of the examination. Maybe the inclination of the magnetic field can play an important role.
What's the propagation speed on the north side? I mean, the propagation direction on the north side?
It's in both sides. I can see the trend is almost the same. It's about I don't know. I can't remember the exact number. It's above 800 meters per second.
But what's the direction? Is there a difference in the direction in the north side and versus the south side?
Yeah, there's a north side and this south side. Yeah.
So that is propagating north and west in the northern side?
Yeah, northern side. And there is a small angle of the phase fronts as compared to the rocket change, about 5 degrees. Not the phase front is not parallel to the trajectory, just like a wave triggered by the moving of the boat along the river. Yes, in the other side also, but here we cannot see directly the north side. You can some very smaller amplitude.
For large scale TID, you said there's one type is westward propagation.
Yeah.
So you said it's not correlated with magnetic activity. So what's the cause of this westward TID?
I see. The main cause of this westward TID is the moving of the solar simulator. And some other authors also observed this TID. In fact, one of my students observed such TID in China. And some authors observed small scale or medium scale TID excited during the sunrise time. And some authors observed large scale, such as Liu Huixin in one of the papers several years ago. I think this is because different filtering method can come up with different results. And as a moving source, it can excite TID with a broad spectrum. And which kind of TID can be observed depends on our filtering measurement. And but there is some difference, because in Liu Huixin's paper, he concluded that the TID mainly caused by during the sunset, not sunrise. But in my observation, I just found that most of them was in sunrise. I don't know why. Maybe because he used TRAMP to observe. I use TEC.
So how far can the propagate in daytime or nighttime?
Uh,
Immediately after.
yeah. In this, you can propagate about several thousand meters per 7,000 kilometers, I think. I don't know what happened in this region because there is a lack of observation.
Another question is how often you observe large-scale TID in daytime as compared to nighttime?
Let me see. This is nighttime, and this is daytime. Maybe in China, most of them was observed during the daytime.
Yeah.
And this is nighttime. This is daytime. Also, most of them happened in daytime in North America. But I don't know why.
Do you know why?
Because iron drag is large in daytime.
I thought nighttime would be more TIDs.
Because iron drag.
Yeah, yes, theoretically speaking, the generation mechanism is more active during the nighttime.
Yeah.
Yes, this is a problem.
Okay, so, yeah.
Yeah.
Question. So did you find any correlation between the strengths of the geomagnetic activity and the strengths of the LSTIDs?
Pardon, please.
The strengths of the source, I mean, you kind of indicated it's correlated to the geomagnetic activity. Into if there's some correlation between, I mean, when they occur and what forcing you need to generate them?
Yeah. In this study, I didn't analyze the one-to-one correlation between the substorm and the occurrence of TID. Yeah.
So is that like when storm is stronger, larger storm, then the TID, there's more TID or larger amplitude?
Yeah, exactly.
Positive.
Because this work, we just get some results of the statistical results. And during the geomagnetic active time, the maximum, the occurrence rate is reaches its maximum during this time.
And
Oh, yeah. Okay. For this plot here, I guess the northern hemisphere, southern hemisphere, the TID are not occurring concurrently, right? They are different events, really. Are you always northern? Do you see the same events, same TIDs for TID triggered by same events, or there's very different events? You often see some TID in the China sector without anything in the north sector. I think it's a mixture of everything, right?
This is a good question. And actually, I analyzed the data separately. And I wanted very much to find same events. But in most cases, I can't find it. Dr. Zhang Shenrong recently published a paper. He said there was a global propagation of TID, and the TID can seen in both North America and Europe and Asia. But I cannot find such TID. The main difficulty is that there is a great local time variation of the background ionosphere. And for example, if here North America is daytime, and in China is nighttime, the background is different, and the TID in most cases cannot found to propagate simultaneously. And another reason is that in my personal view, if there is a source in the sub-L region and excited TID, if it can propagate across the North Pole to the other local time sector, it may endure many variation of the background ionosphere, and this makes it very difficult to propagate across the North Pole and reach the other side of the atmosphere.
Yeah, but I see you said you in 21 months you observe like 300 something events in North America and 300 something in China. So is that the same month, same 21 month, same period?
Same duration.
And it's like almost there's like every 2 days, right? Every 2 days there's one event.
Yeah.
And if this is the same 21 month, then there should be some of the TID events is from the same magnetic storm events because you're doing the same 21 months.
Yeah, I agree with you. There should be some TID occurred simultaneously.
It's the same event.
Yes, it's very possible. I regret I didn't notice that.
It has to be because it's the same.
Has to be.
Yeah.
Yeah.
And also, did you say like there's in China the southward propagating TIDs like occur 1 to 2 hours
after the delay? Yeah.
After what?
After the appearance of TID in North America, in high latitude, because that's the propagation duration from high to mid and low latitude. Yes, it has to. There should be some example. Maybe I can look for the global propagation TID from this case. Yeah, thanks.
Sorry, 2 more questions.
Yeah, please.
The first one is talking about large scale and medium scale TIDs. So how you separate those two? How you define those two? Are they totally different or similar? So how you define those two TIDs?
There are some criteria to distinguish these two kinds of TID as to the velocity, the wavelength, the period. This is the first aspect. As to the second aspect, the LSTID, the primary source of LSTID was auroral activity. And as to the MSTID, there are some localized source. And we distinguish them from both the criteria and the source, the possible source.
In general, what is the separation wavelengths between MSTID and LSTID? 1,000 kilometers, you mentioned 1,000 kilometers for LSTID.
LSTID always has a wavelength, horizontal wavelength of more than 1,000 kilometers. And
could it go benchmark for separating these two?
Yeah. Pardon, please?
Is the 1,000 kilometers is the benchmark separating LSTID and MSTID?
Yeah.
Okay.
And for MSTID, there are always several hundred kilometers.
Is that the MSTID is mostly triggered by the acoustic gravity wave?
I think so. Yeah. And one of my early papers, I didn't show it in this report. So there are also some MSTID associated with plasma instability. Some Japan authors can also observe those, mainly in the low latitudes during the nighttime. Strictly speaking, that was not a wave-like structure, I think.
Usually, how far away can those TID propagate? Can it propagate like from one hemisphere across the equator to the other hemisphere?
Yeah, sure. Many TID can propagate, large scale TID can propagate across the equator to the other hemisphere.
Okay, so is there any conjugacy of the TID occurrence? Like if I observe TID in one hemisphere, you'll be able to observe like in the southern hemisphere as well. The source are both hemisphere?
Yeah, there are indeed some some previous observations of this cross equator propagation. But as to GNSS, because in South Hemisphere there was much less GNSS distribution, so I cannot observe such kind of TID. But I can remember some authors use CHAMP or other satellites to observe some, such as one of my colleagues in Beijing, Guo Jianpeng. He observed the TID propagate simultaneously from both hemisphere aurora region and encountered during the equatorial region. Yeah, and recently, one scholar in Boston College, Pradikta, also observed such encounter of SLTID.
Something well studied, or it's something?
Few study on this aspect, and that's why my students observe the multi-TID. Yeah.
And another question is related to this. So I remember people talking about the more northward or easier for North America sector to propagate to the other hemispheres compared to China, but you observe more northward TIDs in China than in America sector. That's right?
Yeah. I show an example of the Northward TID with a high elevation, and in that case, I believe that taking into account the velocity is rather slow, and taking into account the high elevation, I think it is a localized TID. But in this, let me see, in this statistical results, the black bars here is the Northward TID in China, and they see exhibits a certain correlation with the KP index, and given their propagation velocity, I think they move very quickly. Most of them move very quickly, and I believe most of them were originated from the southern hemisphere.
But why not North America sector? Why is not zero?
Because there was
across the equator large scale TIDs.
yeah, because the magnetic latitude of China is approximately 20 degrees lower than those in North America. Yeah.
Yes, it's damped.
Yeah, damped. Yeah, yes, dissipation.
The observation is mid-latitude in America sector.
Yeah.
Magnetically, that's right. Yeah.
Yes, that's right.